Okay, so today I am going to discuss another interesting problem came in this CSIR net July exam from electrodynamics topic. And this is also a good problem because you need a little bit of imagination to solve this problem. Okay, so here is the problem. The problem says you have a 2D sheet with a uniform sheet conductivity sigma has a central metallic part. There is a central metallic part and a metal contact at the boundary. So at this boundary there is a metal contact, and if a constant current I is injected through the central contact, then collected at the boundary, then what is the voltage difference between 2 points R1 and R2 is proportional to. So the current is flowing through this metal contact and through this sheet, and you have to calculate what is the voltage difference between two radial distances R1 and R2. So look at the picture carefully. When I is injected through this metallic contact, then the current I flow through the sheet in every radial direction. Current will flow in this direction, current will flow in this direction, in all the direction through the sheet. So the first thing that came to my mind actually, so you can write this formula that delta V, the voltage difference is equal to I into integration of dr, where R means resistance. So somehow if you manage to calculate what is the resistance between the points R1 and R2, you will get the answer. Okay. So yeah, so for simple cases, look at a simple case and then you can figure out this difficult case actually. So the simple case is here is a metallic bar and current is flowing in the right side direction. Rho is resistivity, L is the length, and A is the cross sectional area. So for the simple case, you all know that resistance is equal to rho L by A. Now you should keep two things in mind. So look at the direction of the current flow. I is flowing in the right direction. And the length you are considering here in the numerator of this expression is parallel to the direction of current flow. That is one thing. And another thing that look at carefully A, the cross sectional area. The cross sectional area is perpendicular to the direction of current flow. So if you keep these two things in mind, then you can actually figure out then the what is the length element and what is the area element for any complicated problems also, like this problem. So now look at this picture. So as I already mentioned, I is flowing in radial direction throughout the sheet, in all the radial direction actually. So now I am considering a infinitesimal small area of length dr, and this is the arc length r d theta, and this is the thickness t. So I am visualizing a small area actually, small part of the sheet. So this is the cross section. This is the cross sectional area r d theta into t. So small area element actually, and I is flowing in the radial direction. So when I passes through this sheet, the length element is dr. So I passes in the radial direction. So the length element is dr. Dr is parallel to I again. And what is perpendicular to I? Perpendicular to I is this cross sectional area. So what is this cross sectional area? This is r d theta, the arc length, into t. T is the thickness. So theta has nothing to do with r, so you can integrate the d theta. So you can consider now the whole sheet of perimeter 2 pi r. Then 2 pi r is the perimeter, and you multiply it by thickness, you get the cross sectional area. So this is the cross sectional area, and the small length element is dr. So I is flowing through a small length element dr, and the cross sectional area is 2 pi r into t. So now you have figured out what is the small length element and what is the cross sectional area. So now your problem is actually solved almost. So you can now simply integrate what is dr. Dr is integration of r1 and r2. Rho, so in terms of we have given sigma, so you can substitute rho is 1 by sigma. This is the length element, that is dr, and a is 2 pi r into t, where 2 pi r is the perimeter at distance r and t is the thickness of the sheet. So you can now integrate over dr by r, and it is this log r2 by r1. So the delta v is proportional to I by sigma into log r2 by r1. So the correct option will be option 2. So in this problem, you just have to do a little bit of imagination that how we can find the total resistance of the sheet. So if, as I already mentioned in previous case, that if you can figure out that what is the length element and what is the area element, that then you will be done. So you have to keep these two things in mind, that you have to first visualize what is the direction of the current flow, and then you can easily figure out that what should be my length element and what should be my area element. Okay, so this is the technique to solve this problem. And another technique is also you can integrate this as E dot dl. So delta V is E dot dl, and you can write E as J is equal to sigma E. So for E you can write J by sigma, and then you have to write J in terms of uh, this rho L by A, all the things. So yeah, you can do it in this way. So thank you, and if you have any question, then please ask.